Assalamu alaikum wa rahmatullahi wa barakatuh. Today I am here before you to present our work that is titled as a novel large language model based approach for automated Sirah and Hadith mapping that is connecting Islamic historical narratives through vector search and semantic analysis. I am Mushikur Rahman Talha and other authors are brother Muhammad Galib Shams, brother Nabil Musharraf Hussain, and brother Dr. Yasud Islam. Now, let's introduce yourselves to the terminologies that we will be using. So at first, the Sirah is the biography of Hazrat Muhammad sallallahu alaihi wasallam that are mentioned in chronological order. And the Hadith are the sayings, actions, approvals, and advices of our Prophet Muhammad sallallahu alaihi wasallam that are narrated by our forefathers such as Sahabi, Tabi'i, Tabi'in, etc. Linking of the Hadith and Sirah poses some challenges that include large volume of Hadith and Sirah, and we need to handle this information carefully. So we need an automated process that can find relationships between the Islamic texts and make these tasks easier for us. So our objective is to use machine learning techniques like vector search and large language models that can automate this process. So let's dive into our methodology that we have followed throughout this process. At first, we extracted the texts from the database and removed unnecessary words, punctuations, and symbols. This could harm the natural language processing and query. Then we split the Sirah events into several paragraphs, and we tried to maintain the context of these paragraphs of these events. Now, in the tokenization part, we tokenized and created embeddings of all the texts, and we stored the hadith embeddings in the hierarchical navigable small word data structure. This data structure uses the trade-off between accuracy and speed, and we mainly used this data structure because of faster nearest neighbor search. Then we saved the hadith embedding indices, and for each of the embedding of Sirah paragraph, we then carried out the query on hadith indices and saved all the related hadith IDs for each of the paragraphs. And the process is mentioned here as the flowchart. So after this process, we found out a total of 1660 Sirah paragraphs, and for each of the paragraphs, 10 related hadiths were found. That makes a total of 16,600 Sirah paragraph and hadith pairs. Then for each of these pairs, we have carried out a chain of prompts for finding out the match type. Now here is the flowchart of our prompting procedure. In our flowchart, we have carried out 3 prompts, and I categorized all of the outputs as these 5 categories that is given here. So the completes are the above 2 categories, and the partials are marked differently because they need to be manually validated that there may exist some pair that may be considered as complete. This task was the most challenging part throughout our work because we have previously shown you that we have a large number of pairs in front of us, that is 16,600 pairs. This is manually validating this is very hectic task. So we took a sample of only 100 Sirah paragraphs and carried out the prompts on these 1,000 pairs. Among the outputs, we found out that the number of complete matches is 100, which could be manually checked, and we manually checked them and updated the test set along with it. But the number of other matches were very high. Totally 600 no matches were found. So we took a sample of 100 no matches from them and checked them manually and found out that all of them were correct no. That is the LLM responded correctly to the no match types. Later on, we added 50 more Sirah paragraphs to check that whether the process is not biased toward these 100 Sirah paragraphs. Accuracy calculation metric finding is also a bit of challenging, was a bit of challenging task because we couldn't find the accuracy for all of the match types. We only considered with the complete matches since we could verify all the complete matches but not the other matches. So we defined the anomaly of these complete matches, such as those that shouldn't be complete, but the LLM gives output as the complete match. So we carried out two experiments and the results are below. In experiment 1 and 2, we found completes of 119 and 121 respectively. Among these completes, 5 pairs and 6 pairs were mistaken. That shouldn't be complete by the LLM, but the LLM gives complete. And we finally found out that our average accuracy is about 95%. And when we run our process finally, this is the final output of all of the match types. The remaining match types that is not mentioned here are marked as no. So we totally found 1,814 pairs among the 16,600 pairs as complete match and others are the partials. High priority partials are marked because they need to be manually validated later on. In our process, we have limitations of the embedding models because the model that we used here, it is ranked as 42nd in the massive text embedding benchmark leaderboard. And the HNSW data structure that we used creates trade-off between accuracy and speed. So to obtain the speed, we traded off the accuracy a bit. And the prompting in our scenario also has a room for improvement. Finally, before drawing our conclusion, I want to say that our work has provided an automatic system for relating hadith to Sirah that can be further improved. And in our future work, we have figured out some points. That is, we can address the embedding model limitation and the LLM limitation, which can be improved. And the accuracy metric that we have used here, it is not complete reflection of the total work. So there is a room for good improvement in this metric calculation, and manual validation process is also needed. And obviously, we have much more room for improvement in the prompts that we have used. So I want to conclude here. Jazakumullahu khair for being patient. Assalamu alaikum wa rahmatullahi wa barakatuh.
Bismillahirrahmanirrahim, and today I will present our paper, Contextualized BERT Model for Knowledge Graph Completion. The authors of this paper, Haji Gul, Ejaz Ahmad Bhatt, Abdul Ghani Haji Naeem, and we affiliated with School of Digital Science, University Brunei Dar es Salaam, and this paper has been accepted to the third Muslim in Machine Learning workshop at NeurIPS. So actually, knowledge graph is a combination of set of entities and set of relationships and triplet, and each triplet contains 3 parts: head, relationship, and tail. So actually, head and tail, these are entity, and at the middle we have a relationship. So these entities connected by the relationship. Our motivation behind this study is the major problem in knowledge graph. It is knowledge graph completion, because knowledge graph has application in different domains such as NLP, question answering, and healthcare, and this incompleteness knowledge graph, it creates issues, difficulties in these applications. So our aim to improve the performance of knowledge graph completion and to develop a method, such method that improve this incompleteness accuracy. So there are some preliminaries, and actually these are the issues in the existing study. So we will study to understand what are the studies in the existing work. Unseen entity and relationship, those entity which are available in the training set but not available in the testing set, and most of the embedding method they face difficulties in unseen entities like trans e, rotate e, another embedding method. And there is another term, negative triplet sampling. Majority, most of the method like NNKGC and SIMKGC, they use negative triplet sampling. Actually in negative triplet sampling we change head or tail or relationship, and we create a sample, negative sample, and then we train our model like this is the negative and this is the positive, and then we compute the loss. So it actually increase the computational complexity. And there is another term, entity description, which is a full textual paragraph, and some method also use this, but it also cause up the computational complexity. We develop a method based on context aware. So in this context aware we have two main components, head contextual information and relationship contextual information. In head contextual information, our first part is given in the equation number 4. So for the head context we extract all the relationship information, those are connected to the head entity in the first part of HC, and then in the next part of HC head context we have to extract the entity textual information, those are directly connected to the head entity. So now these we concatenate and apply an aggregation function. For simplicity in our work we use simple concatenation function. So now we have a complete HC, and the next part we need to compute the relationship context, which is completely new in the existing literature, and it is not used by the other work. So in relationship context, similarly like the head context, we extract information from the relationship neighboring, and then we combine these information and pass as input to the BERT model as given in equation number 8. Now this is the graphical view of our methodology. In the first left side, this is the head context. We extracted the head context information from blue color circle and red color circle. Blue color the relationship connected to the head, and the green color actually these are the entities connected to the head entity. We extracted and stored an HC variable, and then we have the relationship at the right side. So wherever the R is available, we extract the neighboring contextual information of R and store and RC, and then we pass them as input to the BERT model, but give us some logits, and then we apply the softmax function to extract probability for each tell, and finally we apply the evaluation matrices such as like MR and HitK, and then we get like the proper accuracy and performance rate of different methods. So these are our results, and the main cause behind like why contextualized aware BERT it performed better, it is because of the contextual information of the head and the relationships. And our hypothesis, like if we use the contextual information of head and relationship, what it affect on the performance. So the hypothesis becomes true, and it help in prediction of tail entity, and we have good results. So this is the main insight. In conclusion, actually the contextualized BERT model, this model it is a good contribution in the existing literature of knowledge graph completion, and it has like good performance as compared to other. Thank you so much.
Good day, dear guys. Today I present my research. At first, I need to state my paper is accepted by NeurIPS 2024 workspace, mostly in ML. My topic is reduce the cost, replace the optimization for the chain of sort, reasoning with fast attention mechanism. Okay, at first I need to introduce why I need to do the research. We know that the chain of thought is in 2024. The enhanced ChatGPT, ChatGPT and other large language model accuracy. So this is a chain of thought is also the one task knowledge divides the 5 of 5 or 6, 4 or 5 different tasks and reduce the error, enhance accuracy, and successful. And also, we need to think at the same time we need to think about the divide the 4 or 5 steps. Also, enhance the cost in the LLM. So you see the every the O1 the user can every week can use 50 like this. So this is need to reduce the cost of the cost of the reasoning COT. So in this research, at first we see the article. Article you see it's a sparse encoder layer. Sparse encoder layer is important. We know that GPT series is a decoder only. So this is why I use the sparse encoder. Later I will introduce for you. Explain for you. We can see the sparse attention mechanism is from our brain. So think about one question. How do we thinking quickly about one question? Maybe we want to buy an apple. We need to find the clearly. We need to find the nearest market. So also, what is nearest market is relevant information, relevant token. So based on the exercise, this research also based on the graphic theory base. So also, sparse transformer algorithm also is based on the step-by-step, same as like a self-attention transformer. The most important is this sparse encoder layer. Sparse encoder layer is important. We know the encoder is role to understand the context clearly. So at first we need to understand clearly, and then we can find what is relevant information. So this is the reason is use the sparse encoder layer. So this encoder layer is use a multi-header sparse attention. But the sparse attention is make a thinking speed. So is the harder sparse attention here. We need to pay attention to ON square need less than is reduced to the ON or log n. Log n. This is very important. It's a core technology. But we know we need to achieve this. Need to use the coding. The coding is already attached to my GitHub. So you can see the sparse max isn't the softmax. So softmax is classification, but the sparse max at first need to concentrate on the important information, and then is the classification. Also, you need to see the chain of sort. Chain of sort is between the encoder and the decoder, right? The algorithm is also important, but the most important algorithm. At first, we need to think about the sparse encoder. Sparse encoder is easy. We need to concentrate on the sparse attention mechanism, the method. Sparse attention QK, we know the sparse attention QKV how to calculate, right? And now it have the S is sparse environment, M is the mask. So we need to concentrate about the context and understand and choose the important information. We need to think about the mask and the algorithm. So this is just need to use the mask. Also, the coding is the GitHub. And then into the sparse reasoning state mask. The sparse is RT and MT. And the final decoding output. This is the algorithm to the pretext. We need to prove that it's a truth. Also, in user experiment, is search use the Green Rabbit. Green Rabbit is trained is customer GPTs. The customer GPTs is GPTs is with a sparse attention with open preview COT. So also when you compare the different metrics, resistance time and the correct source score and the COT length. So it's very important. And how to How to experiment the dataset. Dataset is MIT, the open course view, have the liar and train barrel. Why use choose this when using the master question need to think about one step by step. We can see that clearly the ability to the model. We can see the sorry. We can see the data analyzed. At first, the zoning time, you see, the open preview have a very long time, but the green rabbit have a very less time. It's reducing the course, right? And the uh, collect scores, of course, O1 is higher, but the COT less also is less than green rabbit than the O1 preview. Also, you can see clearly the time and the aggregate score and the step. Also, this have the limitation. The limitation in GPT, customer GPTs, the current rapid, because the OpenAI the base knowledge now is December 2023. We can regard as the GPT-4 Turbo. So it's a different model, maybe have a different setting. But also we have the successful data analyzed. The conclusion at last conclusion we can prove the green rabbits have the less resting time and the TOT less than OpenAI O1 preview. So also it gets the objective. Okay, that's all. Thank you so much.
Hello everyone, it's an honor to be here at NeurIPS 2024 Muslims in ML workshop, presenting our titled work GREC Knowledge Expansion in Material Science. This work has been accepted to the third Muslims in ML workshop co-located with NeurIPS 2024. Material science is a field that relies heavily on precise and up-to-date information for innovation. However, when we look at the tools available today, particularly in LLM field, where we can integrate the retrieval augmented generation, which also known as RAG, we see significant limitations. These models can retrieve outdated or irrelevant spatially information, struggle with hallucination, and fail to provide sufficient interpretability, especially in our domain. Our goal with this research was to overcome these challenges by leveraging the strengths of graph databases and improving retrieval accuracy and contextual understanding. And that's what led to the development of GREG. Okay, let's start by understanding the problem we set out to solve. Current REG approaches, while powerful, rely heavily on unstructured knowledge bases and simple retrieval pipelines. Although there are many advancements right now happening in the RAG field, but still uh, there is a lack of having a proper pipeline. This limits their ability to provide reliable, contextually relevant answers, particularly when dealing with extensive specialized domains like we have right now in material science. For example, traditional systems may return a mix of relevant and marginally useful information, diluting the quality of the response. We identified this gap and realized the potential integrating of graph-based approaches to enhance both the retrieval and generation processes. Our proposed solution is a graph-enhanced retrieve augmented generation system designed specifically to tackle these issues. The core idea is simple. Instead of relying solely on text chunks, we employ a graph database to store entities. Here we are making the term as mat IDs and their relationships. These entities are extracted from material science documents through advanced entity linking and relation extraction techniques. The graph structure allows us to capture the rich semantic relationships between entities, enabling more precise and context-aware retrieval. Our defining features of Jurek is the integration of external knowledge base. Especially for this part, we are using Wikipedia. Here's how it works. After parsing a document, we identify key entities such as material properties, compositions, and experimental results using our span parser module. These entities are then used as queries to retrieve additional information from the Wikipedia knowledge base. By tapping into the Wikipedia's vast and continuously updated repository, we enrich the graph database with contextually relevant data. These steps ensure that the system is not constrained by static nature of internal data, but remains dynamic and comprehensive. Our pipeline begins with PDF parsing, a critical step in material science where data comes in diverse formats, including text, figures, and tables. We utilized advanced tools like Visual Instruct models for figures and Microsoft's Table Transformer for table data. This ensures that all relevant information is parsed accurately for downstream tasks. We also introduced some agents to validate that our parsing is happening very perfectly or successfully. So here is the overall methods of how we are parsing all the PDF, PowerPoint, and all the text file, and then also figures and tables, and then all the chunking, and then operating all using agents, and then validating the process. Here the span parser identifies key entities, and the passage processor integrates these entities into a coherent graph structure. By connecting their entities with their semantic relationships and supplementing them with Wikipedia-derived knowledge, the graph database forms a foundation for highly targeted information retrieval. The span parser is the initial component of Jurek system, designed to extract relevant entities and relationships by comparing semantic similarities. It encodes both the current knowledge base and external passage, such as Wikipedia, into high-dimensional embeddings. The similarity between the query and external passage is computed using a dot product embeddings. The module ranks and retrieves the most relevant passages, ensuring precise and targeted information retrieval for downstream tasks. The passage processor processes the retrieved passages alongside the existing knowledge base, combining them with structured input sequences. It uses transform models to generate contextual embeddings and identify relevant spans within the combined data. By calculating probabilities for start and end tokens of the spans, the module ensures accurate text segmentation. This facilitates robust entity linking, relationship extraction, and integration of knowledge, external knowledge into the system. Here is also the retrieval process from the graph database, where we are using also the LLM, and here we are using the llama index for all the processes. What sets Jurek apart is its ability to balance the accuracy, faithfulness, and relevancy. Unlike traditional RAG systems that struggle with limited context windows, Jurek ensures the most critical nodes and relationships are queried from the graph database. This keeps the information concise and relevant, even with the token constraints of current LLM. For instance, when retrieving the yield strength of material at specific temperatures, Jurek doesn't provide numbers. It contextualizes these values with the information about grain size, thermal effects, and compositions. This is invaluable in material sets where precision is paramount. To evaluate GRAG, we designed a dataset of 10 domain-specific queries covering complex material science topics. Our experiments compared with NaivRag, GraphRag, and GRAG on metrics like correctness, faithfulness, and relevancy. The results were striking. GRAG improved correctness on scores by 60% compared to the NaivRag and demonstrated superior context relevancy. For example, in a query about the yield strength of an alloy, provide accurate contextual responses that align closely with the ground truth data. This level of precision highlights the transformation potential of graph and enhanced approaches, particularly with the added depth of Wikipedia integration. So that's our presentation. Thank you all.
Good morning, everyone. This is Naushad Shafi. I'm here to present a paper entitled ComRiad for Alzheimer's disease detection. Myself, Naushad Shafi from Department of Computer Science, College of Science, Sultan Qaboos University from Sultanate of Oman, co-authored by Mufti Mahmood from KFUPM, Saudi Arabia. This work has been accepted at the third Muslims in ML workshop co-located with NeurIPS 2024. Traditionally, Alzheimer's disease detection using deep learning has been carried out by considering any of the single planes. For example, the dataset can have MRI dataset can have coronal plane or axial plane or sagittal plane. So far all the works, most of the works have been carried out by considering any one of these planes only, and mostly axial planes, because the traditional datasets that are available in the public platform is considering only axial planes. So in this work, what we have done is we try to combine all the three planes of a subject and applied deep learning algorithms on each plane, and we try to combine the results of these planes to enhance the classification performance of the deep learning frameworks. So the main contribution here is we propose a novel deep learning based pipeline called ComRiad, which combines three planes, coronal, axial, and sagittal, and we referred it as combi-plane approach for enhanced Alzheimer's disease detection and classification. Our experiment results demonstrates that ComRiad outperforms single plane MRI analysis, achieving at least 6 to 8% increase in overall accuracy for two-way as well as four-way classification task. So we have performed both classifications, binary classification as well as four-way classification of Alzheimer's disease, trying to detect different stages in dementia. The four stages are Alzheimer's disease, which is the end stage of the disease, and then in between we have mild cognitive impairment, MCI, late mild cognitive impairment, and cognitively normal. So these are the stages of this dementia disease, and we are doing both four-way classification as well as binary classification, given an image whether the patient have Alzheimer's disease or no. So this is the pipeline you can see here. Traditionally, the patient undergoes some kind of scanning. Scanning can be PET, fMRI, MRI, and once the images are obtained and the models are trained, so this box indicates some deep learning models, different architectures. So in our case, what we have done is we have taken the convolution neural networks and especially the MRI block. So here the highlighted block indicates the actual contribution of our paper. So what we have done is we have taken out of all these biomarkers, we have considered 3D MRI, and from 3D MRI we obtained all three planes, and on individual planes we apply convolution neural network and we get the classification results from each plane. Now the classification results are actually combined to get the final classification results. And also, as you can see here, to enhance or to get the interpretability of the results obtained by this deep learning networks, which is often considered as black boxes, we consider the final convolutional layer and we obtain GradCam heat maps, and we try to obtain some affinity between the heat maps obtained with the predicted labels. So this is the experimental result. First, what we have done is we have considered the ADNI dataset for experimental purpose, because ADNI dataset has not only the three planes of MRI for every subject, it has all the clinical parameters and different biomarkers like CT scan, PET, and clinical datasets. So we have considered MRI ADNI dataset, and from that we have considered MRI planes. All the three planes we have considered. So what we have done is once we have extracted the MRI images, we split the dataset into 70 and 30%, 70% for the training dataset and 30% for the test dataset. You can see here 70% of the data has been trained, and from the remaining 30%, what we have done is we created triplets of the images from each plane, coronal, axial, sagittal. That is actually this combi plane. Individually as well as combi plane wise also we have extracted the results. So individual results are for every plane is noted down here in this table. And what we did is like the triplets that we consider from each plane to form the test base for the combi plane approach, we increase it in terms of 1000, 2000, 4000 and 8000, and you can see here the combi plane approach significantly outperforming the individual plane approach. You can see here by at least 6 to 7, 6 to 8% of increase we can see here, not only in the accuracy as well as other performance metrics like specificity, sensitivity, false negative rate, false positive rate. You can see here false negative rate and false positive rates are significantly low in the combi plane approach for different number of input cases. Now this image shows the combi plane approach confusion matrix. You can see here this is the confusion matrix drawn for 4000 images. Coronal plane has the confusion matrix of this, and sagittal and axial planes also obtained confusion matrix of these figures. Now using the combi plane approach, this is the result of the confusion matrix obtained when we combined all the three planes. You can see here there is a significant increase in the correct classification of the four classes. So this result shows that the combi plane classifier considers the subtle patterns that are observed from all the three planes and combines them to make a more accurate classification for the Alzheimer's disease. And also when we go to a clinician will not only see a single plane like the traditional deep learning platforms carry out the task. So we are trying to do what clinicians traditionally do. They take the MRI and they see the disease pattern from all the patterns. So we are trying to mimic what the clinicians do to diagnose the neurodegenerative diseases like Alzheimer's disease. Okay, so here this is an example experimental result for binary classification of the disease between different dementia stages. You can see here the first one is about early mild cognitive impairment versus late mild cognitive impairment. The easiest binary classification is between Alzheimer's disease and cognitively normal cases. What is more difficult is to differentiate between the stages of the late stages of the dementia like MCI and EMCI. It's very subtle different. It is very difficult even for the clinicians to observe the pattern or to tell in which stage the patient is currently undergoing. If you can see here, the green bars indicate the results obtained by the combi plane approach. You can see here the false positive rate, false negative rate is significantly low in every binary classifications that we have carried out here. Now this is to the clinicians will be only happy if they know why some results are why some results are coming in that manner. For example, they know it has been a particular image has been classified as Alzheimer's disease, but they should also know the associated reasoning behind that classification by the deep learning framework. So here we try to extract some explainability, and we applied GradCam explainable interpretability framework for generating the heat map. And what we observed here is the red regions in the overlays. So this is the heat map from the GradCam, and when we overlaid this heat map on the original image, we get this third row images where red regions in the overlay signify a close affinity to the predicted class. The axial plane here highlights regions associated with neurodegeneration, atrophy, or abnormal metabolic activity in Alzheimer's disease. The coronal heat map here focuses on cortical areas like the temporal and parietal lobes commonly affecting in the Alzheimer's disease. And finally, in the sagittal plane, the red region highlights vulnerable regions like the prefrontal cortex and posterior cingulate cortex. So by examining all the heat maps, clinicians can gain insights into how the results affect the AD-related changes in the brain. We also computed paired t-test to test the significance of the results. The obtained p-values here in the last column imply high statistical significance, confirming increased reproducibility of the method and reflecting a consistent pattern of the results rather than the results coming as a random chance. So this statistical test confirms that the pattern of results are consistent and they consistently outperform individual plane approaches. So the key findings here are the increased accuracy of 6 to 8% compared to the single plane approach, and also we conducted paired t-test to test the significance of the results. Heat maps generated using RADCAM and Pearson correlation coefficient computed between the original MRI and heat map show high affinity to the predicted class. There is one limitation to this approach, which is increase in the computational cost associated with the processing multiple planes to achieve enhanced accuracy. So multiple plane means increased resources in terms of increased number of parameters, the memory and computation to learn those parameters, storage and deployment in real time. So this is all some real time limitations of the proposed approach, but some kind of optimization could be incorporated in future work to mitigate these limitations. So this is about our work, and please feel free to contact us for any questions that you may have, and also we have provided GitHub link for our code. Those codes should help reproduce the results that we have reported in this paper. Thank you.
Hi, today I'll presenting our work on multimodal pipeline defect localization, a collaborative effort by Mariam Manzoor, Zahra Arabi-Nouri, Henry Leong from University of Calgary, and Scott Miller from Baker Hughes. And this work has been accepted to the third Muslims in ML workshop co-located with NeurIPS 2024. About the motivation, pipelines are essential for transporting oil and gas, and ensuring their safety and reliability is crucial. There are two common non-destructive evaluation techniques, which includes laser profilometry and magnetic flux leakage, as we called it, MFL. For laser profilometry, it provides high resolution, precise defect shapes, and on the other hand, magnetic flux leakage detects pipeline anomalies by analyzing disruptions in magnetic fields, which making it ideal for larger scale inspections. Integrating these two methodologies helps us to get the higher accuracy profile defects in larger scale inspections. But it will introduce challenges like data misalignment, label noise, and domain shifts between laser and MFO. And this motivated us to explore the performance of state-of-art model to address these challenges. Our contribution include analyzing the challenges of integrating MFL and laser data, evaluating how label noise and domain shift affect state-of-art models, and providing insights into the limitations of current approaches.
We started off with labeling our dataset. Our dataset consists of 33,000 samples, where each sample contains a laser image and triaxial MFL signals. And the MFL signal include a signal in axial direction, a signal in radial direction, and a signal in circumferential direction. To define defects, we use laser data as ground truth, and we generate defect masks and bounding boxes using Ortsu thresholding. We also apply data augmentation techniques such as translation, zoom, and horizontal flip to improve our model's generalization. On this slide, you can see an example of the original laser image, the MFL axial signal, radial signal, circumferential signal, and the combined 3-channel input, along with the defect mask and bounding boxes we detected from Ortsu thresholding. Our primary framework for defect detection and segmentation is MusCarCNN with a ResNet-18 backbone. The MFL data is the input for our model, and the bounding boxes and masks derived from the laser data serve as our ground truth. The primary objective is to detect the defect profiles as close as possible to the original defect of the pipeline, which is represented by the laser image. In our evaluations, MusCarCNN outperformed YOLO, particularly at higher confidence thresholds, which is also visible in the table shown in the slide. Interestingly, using ResNet-18 with FPN did not significantly improve the F1 score compared to using a standard ResNet-18 backbone. An interesting observation in that table is that the recall rate across all confidence threshold is low, which highlights the persistent challenge in reliably detecting all defects close to ground truth. One key issue, which is also visible from the sample shown in the slide, is that the defect with lower confidence score often are filtered out as false positives during evaluation. Our model is not confident in differentiating noise, which looks like a defect, from the actual defect. Moreover, the mismatch between ground truth region and input feature patterns reveal complexities beyond alignment or box size discrepancies. For example, in this sample, the false positives actually sometimes represent the defect, but they don't exactly match the ground truth by the laser. They have they are smaller boxes within a larger box and have very low IOU, which is our metrics for comparing the ground truth with the predicted boxes.
For the segmentation part, first we try to evaluate the outputs of mask CNN. As we saw the discrepancies in the outputs, we try to analyze other segmentation models that doesn't based on region proposal approach. We tried unit and different variations of units, like adding attention gates and using the transformer-based encoder for the unit. You can see the scores of dice, Jacquard, and accuracy for all models here in the table. Although scene units are outperforms Mascar CNN in dice and Jacquard scores, but you can see the results remain unsatisfactory, and we see all consistent discrepancy in all models that I'm going to explain in the next slide. Here in the figure, you can see that the first row we have the 3-channel MFL image, and the second row is the laser one, and the mask which is extracted based on auto thresholding is overlaid on the laser one. And the predictions of two models, Swin Unit R and the mask CNN, are obvious in the figure. As you see, we have some discrepancies that come from a domain gap between laser and MFL signals. And the defect characteristics in MFL doesn't have point-to-point mapping with the laser-based ground truth mask. And also, we have inaccurate ground truth annotations from laser images. And as you see here, it fails to precisely define defect regions and boundaries for samples, which introduce label noise, and it somehow hinder model from capturing meaningful patterns and overfit on the nodes. For the conclusion part, we analyze the performance of different models on defect detection and segmentation, explore the effect of label noise and domain shift, and also we show that because of this misalignment between MFL and laser, the state-of-art models can perform well. For future work, we will focus on modifying loss functions, exploring domain adaptation techniques, and noise-robust architectures to improve defect detection and segmentation performance. Thank you.
Assalamu alaikum wa rahmatullahi wa barakatuh. This is Toibo Guremi, and I will be presenting this work on behalf of the co-authors, the neural machine translators as efficient forward and backward Arabic translators. This is a joint work that is accepted at the third machine learning workshop, Muslims in Machine Learning Workshops, co-located with NeurIPS 2024. So the agenda of our discussion for today is on the following. It will contain all this that was listed here. So the background of this work is that to explore non-Latin writing system, because we found out that there are about 48 commonly used global writing system in the world. And Arabic is a unique one with 28 letters that is written from the right to the left. So translation is a process of converting words or text from one language to the other while maintaining the literal meaning of the original words. While transliteration is a process of converting words or phrase or expression from one writing system to the other writing system, most especially the non-Latin writing system to the Latin writing system or Latin script, while maintaining the sound of the original words. So example is the picture that is image shown here, where we have Bab, Kataba, and Nabil here. So the transliterations of these words in Arabic writing system to Latin writing system is followed here, while the translation, which explain what they mean in both languages, is what we have in the open brackets and the curly brackets under here. So the motivation for this work is to explore the discontinuity between Arabic and other writing systems like non-Latin Arabic is a non-Latin, while we compare it with the Latin system. So the other one is to investigate and enhance the ability of non-native Arabic speakers in typing and reading Arabic content. Then the other one is to improve on the findings of authors that found that Roge evaluation is very poor on non-Latin scripts. So the other one is that we found out that transliteration is a better approach for non-Latin writing system because there is a typing ease, since most keyboards offer these letters that are required for transliteration. The other one is that non-Latin languages is easy to learn for foreigners that are already familiar with Latin scripts. The other one is that communication, whereby majority of people use transliteration to communicate worldwide on social media platforms, and most religious knowledge resources now have transliteration embedded uh, into their knowledge box. So these are existing challenges and use case. We can see that this is an Arabic keyboard, which is not usually easy for most people to type in, as we can see that there are even some missing letters in the keyboard that for a user to type, they have to make some other combination of words before they can be able to get there. While this one is trying to bridge the letters in Arabic with the the pronunciation of them in Latin system. This is a transliteration of Arabic from Arabic to a Latin system that is in transliteration, while this one is just the translation in Urdu. And then here we have a popular language learning platform, Duolingo, where we can see a bridge between Arabic letters and their Latin script equivalent. And this is for communication on social media platform where users try to communicate Arabic using Latin letters or Latin writing system. And this is a religious knowledge box where we have Quran text being written in their transliteration form to aid non-original Arabic speakers to facilitate their reading. So our contribution is to help in the existing challenges. We saw that there is lack of parallel Arabic romanization scripts. Most problem where user face is that there is no parallel Arabic transliteration data set to train models to be able to learn the correct mapping or relationship between Arabic letters and non-Latin and their Latin equivalent. Then there is inconsistencies in the representation. In some cases, we found that some letters are represented with different characters, which cause a lot of incontinuity. So the other one is no standard one-to-one mapping or relationship between the letters, Arabic and the Latin characters. And their variability due to dialect and informal usage. Various ways people use their own is different from the way another person uses. So what our own contribution is that we have curated an Arabic and translation script dataset using the Excel sum, which has the Arabic writing system, and we use the U-Roman tool to romanize it into the Latin equivalent of those letters. So we propose and develop a proof of concept to show that actually neural machine translators can effectively convert back and forward, whether from Arabic to Latin script or from Latin script to Arabic. And then the other one was to compare the state-of-the-art model performances using the Blue and Roge evaluation metrics. So we are hoping that possibility of a unified keyboard for all languages, because if transliteration is made available, then we can be able to use a single keyboard to type any language. So various related works in this regard are that Chakachiro in 2010 highlights some effect of inconsistencies in romanization practices by saying that it usually affects the preservation of the Arabic letters and Arabic contents. The other one is by Chalabi and Judges, where they built a system to be able to convert from transliterated text into the colloquial Arabic. And M. Jacob developed the Euroman, which is a forward-only romanization tool that converts from Arabic to Latin scripts. So they were trying to make a uniform way that rely on Unicode that converts from Arabic to Latin characters. So where J et al. In 2024 use romanized text as an intermediary when using large language models to learn non-Roman scripts, because they found that they benefit from the shared tokens, since the letters are quite similar to English, and they can benefit from English pre-trained LLMs. So our methodology is that we got the data from the Excel sum, which has the Arabic part, is originally made for summarization, and the pre-processing was done using the Euroman tool that was developed by MJ Corp. And then the training, we fine-tuned 3 Hugging Face machine translation models using the following parameters, and these are the pre-trained language models. So these are our key results. We found out that all the models quite perform well by having a Roach score and Blue score of above 90, and then the difference in the generation length is possibly due to the out of the box vocabularies that the tokenization has, since it's not really familiar with the transliteration as a separate language before. So by analyzing the predictions from the models, we found out that these are some of the mistakes that the misgeneration or the wrong generations in the model. For the Latin, the model quite performed well. Only this was the error that was made. While for Google MT5, which performed poorly on this, this is the worst prediction in generally, as most of the model predicted correctly in 3185 sample out of the 4689 test data set that we evaluated them on. So in conclusion, we hope that this a uniformed forward and backward transliterator system for Arabic using the NMT, the neural machine translators, and future work will seek to expand this transliteration to cater to full romanization, which involves representing the graphemes and phonemes, because most of the examples that we have found in the data set is that they omitted the graphemes, like the tonal marks of the letters, because in Arabic we usually have the upper, the middle, and the sukun, the afatiyad, all those marks were omitted. So in a way that would expand, that would cater to all these ones too, would definitely help the Arabic transliteration. Thank you very much.
Hi, my name is Alshafatak Silvi. I will be going through our paper Deep Learning in the Wild for Industrial Scale Plastic Waste Sorting, which has been accepted to the third Muslims in ML workshop. This project is funded by the US Department of Energy and developed in collaboration with Purdue Fort Wayne and UHV. Let's start by an overview of current plastic waste problem. As the world relies more on plastics, large amounts end up in oceans and landfills. Low-density polymers break down into microplastics. These microplastics spread through wind and causes serious environmental pollution. On plants, it impacts their growth, development, and photosynthesis. In aquatic life, it builds up in the hearts, intestines, and gills. Additionally, cardiovascular diseases in human animals are directly connected to microplastics. Wealthy countries dealt with their plastic by exporting it to China. After China's sword policy, these countries shipped their plastics illegally until 2022. The graph in the right corner shows the change in plastic waste exports to non-OECD countries over time. To top it all off, the widespread use of plastics has fueled remarkable economic growth in the global market. Currently, material recycling facilities rely on a combination of manual, semi-automated, and fully automated sorting systems. These systems utilizes manual labor, NIR, XRF, and vision-based technologies. However, semi-automated sorting remains the most prevalent. Challenges such as the low market value of plastics other than PET and HDPE, health risks to human labor, and issues with contaminated or dark plastics persist. MRFs report that 35% of colored plastics are incorrectly sorted and 5% of sorted bales are rejected due to contamination. As our project is to recover municipal solid waste, we focus on current viable datasets on MSW. But unfortunately, at the time, we only found 3 datasets which offer exceptionally low number of samples for the scale of this problem. On the other hand, recent approaches to the plastic sorting have evolved from traditional spectral-based methods to sophisticated ML solutions, but these approaches still lack real-world deployment. Our dataset stands as the most comprehensive collection of plastic found in municipal solid waste to date. The materials were sourced from the Solid Waste Authority in Florida. While our initial collection included 10 material categories, including all plastic types, aluminum cans, paper, and mixed plastics, this project focuses specifically on 5 types of plastics. The data collection process was semi-automated. Initially, we sorted the first few bales by hand and consulted with plastic experts for evaluation. Once trained, the EcoSorter took over the data collection process, improving its performance through iterative training over time. Ambiguous cases such as scratched or contaminated plastics were sent to the NIR facility at INL for precise identification. Finally, we curated 3 variations of this dataset. The EcoSorter stands out due to its integrated pipeline, which simultaneously classifies and collects data. After collection, the data is utilized for further classifier training. The pipeline is designed to be scalable and modular, allowing for easy adjustments as needed. We trained classifiers on all dataset variations and selected the normal dataset for deployment. To ensure robust classification, we implemented target data augmentation for underrepresented classes. Given the constraints of the EcoSorter, which is equipped with an 1080 Ti GPU, we needed to ensure that our models were both compatible with the hardware and capable of real-time performance. After extensive training and fine-tuning of 4 different architectures on our dataset, we developed a modified ResNet 50 which achieves an accuracy of 87.19% in 0.181 millisecond. To address the challenges of dark plastics, we utilized yellow V5 for finer segmentation, ensuring that materials are accurately prepared for the classifier based on their training data. Yellow V5 was specifically employed for segmentation due to the complexity of the classification task and the need to optimize inference time. One of the key challenges in plastic sorting is addressing the impact of deformations. Deformations alter the visual and spectral features of plastics, although their fundamental characteristics remain unchanged. Our experiments on plastic deformation aim to understand how the model performs under these conditions. By incorporating more data and introducing more variability, we evaluate the model's ability to improve. We trained 3 models using 50%, 75%, and 100% of type 7 objects, which primarily consist of Arizona teachucks. This approach provides insights into how the model handles both pristine and deformed materials. The model trained on 50% of the dataset resulted in only 51% accuracy on unseen data. Expanding the dataset to 75% improved accuracy significantly to 89.93%, while using the full dataset further increased accuracy to 93.75%. This demonstrates a misclassification reduction of 11.4% from 50 to 75% dataset size, compared to only a 0.99% improvement from 75% to 100% dataset. In conclusion, the diminishing returns observed between 75% and 100% dataset utilization highlights that the marginal gains do not justify the additional time, energy, and financial cost of further data expansion. TSNE and GradCam was utilized to have explainability of the models employed in EcoSorter. TSNE helped us understand what our dataset lacked and what could be improved. On the other hand, GradCam gave us critical information on misclassified objects. With more explainability, EcoSorter's pipeline ensures it is ready for industrial cases. Finally, our proposed sorting system demonstrates commercial viability by processing 200 samples per hour with a potential cost of $30 per ton. It requires minimal labor and ensures 5 types of plastics are sorted and data collected. This work establishes a foundation for future improvements through synthetic data generation for underrepresented plastic types and continuous learning mechanism for dynamic adaptation to new materials and deformation. Thank you.
Hello everyone, my name is Mohammed Fares and I recently completed my master's at Istanbul University Jarrah Pasha. I am presenting this on behalf of myself and my co-author Ahmad Saad. We are happy to share our research on privacy-preserving medical imaging. I'm also pleased to mention that this work has been accepted at the 3rd Muslims in ML workshop collocated with NeurIPS 2024. As AI use in healthcare grows, concerns about patient privacy become critical. Protecting sensitive medical image ensures patient trust and compliance with regulations. However, privacy concerns also limit data sharing, which is essential for training effective deep learning models. We focused on federated learning and differential privacy for robust privacy protection. Federated learning allows decentralized model training, keeping data local while only sharing model updates. Differential privacy introduces a controlled noise to data, making it harder for adversaries to reconstruct sensitive information. The secure multi-party computation protects model updates during aggregation, enhancing security and scalability. Building on these techniques, we developed a framework for privacy-preserving federated learning system. The federated learning system combines federated learning with local differential privacy. And the secure aggregator prevents the curious server from accessing individual updates. We also introduced differential private ResNet architecture, a modified ResNet 9 optimized for differential private applications by replacing patch normalization with group normalization and removing max pooling layers to enhance efficiency in these settings. We evaluated our framework using the blood image dataset, a benchmark for medical image classification. Data was partitioned non-IID across 10 and 20 clients, mimicking real-world heterogeneity. Each client receives between 0.45 times n and 0.55 times n samples, where n is the average sample count per client, mimicking imbalanced federated settings. We tuned the gradient clipping value. 5 was too small, sacrificing accuracy. 10 was too large, providing minimal privacy. 7 achieved a fine balance between accuracy and privacy. The Secure Aggregator Plus used a reconstruction threshold of 4 shares for secure aggregation, which basically represents the minimum number of shares required to reconstruct a client's private key. We tested this on 3 configurations: without differential privacy or secure aggregation, and with only secure aggregation without differential privacy. And the 3rd configuration was using both techniques, differential privacy with secure aggregation. Our results showed that proposed framework, differential privacy with secure aggregation, achieved accuracy less than only 1% of non-private settings, outperforming Premia and FedMIC, the state of art in this domain. In conclusion, our framework combines differential privacy and secure aggregation for robust privacy protection and utilizes a modified RESTnet architecture for differential private applications and non-IID data. The framework also achieved competitive accuracy compared to existing methods. Our framework advances privacy-preserving machine learning in healthcare, offering a secure and effective solution for medical imaging. Thank you very much.
Assalamu alaikum. This work has been accepted to the third Muslims in machine learning workshop co-located with NeurIPS 2024. This work is about three-dimensional localization and autofocus of the particle field based on deep learning and depth from defocus. My work is about the following part. As the first is the background. Particle field positioning is very important in many areas such as the environment and the biology. Now this work is about tracking the dust, and this is single particle tracking in real time. However, it meets some challenges. The main challenge is how to determine the depth. In the traditional method, depth from the deep focus is used. Look at this. The red blood cells at different defocus distance show different images. So we can get its depth from the image. But the traditional method must with the focus criteria. Must work with the criteria. Is quite complex. Deep learning based methods was thought to have more to have a better efficiency. Our method works with deep learning method. Look at this. This is the workflow for the three-dimensional positioning and autofocus imaging. At first, we should collect a lot of data, and for training the positioning network YOLO, we use the label image to give them the ground truth, and then training the YOLO. The dataset can be also used to train the GAN. With the trained network, trained YOLO, we can get the three-dimensional position for the particles, and with the GAN we can get the focused image of each particle. The work was validated with the simulated data. The data is generated by three-dimensional ray tracing way, and we can find that the predicted depths match the set depths very well. The accuracy rate is about 99.9%. However, look like this. The overlapping of the particles may cause some errors. We also use the method to the static field. The ABDE is about the standard polystyrene particles. The standard particles, for the standard particles, the accuracy rate can be as high as 99%. And the other image is about the red blood cells. However, owing to the noises, the accuracy rate was about 97.8. We also used the method to the dynamic field. Look at this. It's a standard particles in the oil. We can see that the positions of each particles moved in this way. Following this, we can see the oil flows in a laminar manner. We can also use this method to monitor the planktons. This is the plankton. We catch them from a lake. We can see that the opposite of the plankton swim irregularly. Despite this, the autofocus can also help us to see the plankton in each moment. Also, we can see the particle in the particle field clear with the autofocus. We implement the autofocus method following this way. First, generate a parity dataset by circle GAN. Then, train the pix-to-pix scan using the generated dataset. Then, get the focused image from the defocused images with the help of the trained pix-to-pix scan. We can see that with our method, the trajectory of the plankton and clear images at each moment can be obtained even with a common microscope. Despite this, our work has been expanded and engineered for application in remote sensing. It has already been implemented in transposition, resource exploration, and other sectors in China. This is the work, and this is the UI. I'm sorry, I use this in Chinese because our work is mainly used in China. I hope in the future we can cooperate using deep cooperate using deep learning as well as our satellite resources. This is our work. This is acknowledgement. This work was supported by the government of Hebei province of the People's Republic of China, and was supported by our non-Muslim colleagues, Professor Wang, Dr. Wang, Miss Zhang, Miss Wang, Mr. Wang, and Mr. Hu, and Miss Su. Thank you for your attention. I look forward to potential cooperation in the future. Thank you. شكرا جزيلا.
Hello everyone, I am Alif bin Abdul Qayyum and my co-author is ANM Nafiz Abir. Both of us are PhD students at Department of Electrical and Computer Engineering at Texas A&M University, College Station, Texas. I am going to present our work, Physics-Informed Model-Based Reinforcement Learning for Controlling Synchronization of Weakly Coupled Kuramoto System. This work has been accepted to the third Muslims in ML workshop co-located with NeurIPS 2024. Kuramoto model is a representation of collective dynamics such as neurobiological systems. It is a network of different oscillators coupled with each other through a coupling coefficient value, and the behavior of the overall model is governed through a bunch of coupled differential equations. Usually, when the coupling coefficient of the overall Kuramoto model is lower, then it is a weakly coupled Kuramoto model and it tends to behave in an unsynchronized manner. To control the overall Kuramoto model, we need to apply control signals to each of the oscillators. However, controlling such a complex system like Kuramoto model is challenging due to various reasons. For example, if we want to apply control signals to one specific oscillator and try to synchronize it, it might disrupt the frequencies and phases of the other oscillators, and the overall system may get unsynchronized. Also, when the overall Kuramoto model is larger, there are a large number of oscillators in the model. It's more difficult to control such a model. We use reinforcement learning for this problem, and the overall reinforcement learning problem formulation looks like this. We have an environment, in this case is a Kuramoto model. The states of the environment are the angular phases of all the different oscillators. We have an agent that tries an action, and the action in this case is the control signals to each of the oscillator. After applying the control signals, the phases of all those oscillators change, and the overall synchronization status of the environment changes. And from the synchronization status, the agent gets a reward depending on the synchronization status of the overall model. And that's how the overall reinforcement learning problem formulation work for this work. We used three different kinds of reinforcement learning approaches. The first one is a model-free reinforcement learning. So here we don't have any model that tries to imitate the underlying environment. In this case, it is a Kuramoto model. We used twin delayed deep deterministic policy gradient method to train the agent. We also used model-based reinforcement learning, where we have a model that tries to imitate the environment, in this case, which is a Kuramoto model. And we use generated data from that imitating model and also the data collected from the actual environment to train our agent. Usually, we use reconstruction loss between the generated data and the collected data to train the imitating model. In the physics-informed model-based reinforcement learning case, we use physics-informed residual loss apart from reconstruction loss to imitate the environment, aka the Kuramoto model. The goals for all the experiments done in this work is to enhance the sample efficiency. That means we want to use lesser number of samples or explorations to train the agent so that it can take optimal action or it can apply optimal signals to control the overall Kuramoto model. We use two different kinds of Kuramoto models, one with 5 oscillators and another with 10 oscillators. To make the uncontrolled Kuramoto model unsynchronized, we use a low value for the coupling coefficient, which is 0.01. These are some results. Here, the RM value shows the ratio between the generated data by the imitating model and the data actually collected from the environment. And we can see that both the regular model-based approach and the physics-informed model-based approach outperform the model-free approach. These results are for a smaller network with 5 oscillators. For a larger network, we can see that the highest reward got by the agent becomes less frequent compared to a smaller Kuramoto model with 5 oscillators. For a larger network, what we see is for some cases, when the ratio between the generated data and the collected data is smaller, all the different reinforcement learning methods perform quite similarly. However, when the ratio gets higher so that we are using more synthetic data, those data generated by our imitating model, our proposed physics-informed model-based reinforcement learning method outperforms the other two methods. So the key takeaways we can say in this work is for a smaller network, the regular model-based reinforcement learning and the physics-informed model-based reinforcement learning perform quite similarly. However, for larger network, having a physics prior actually helps to learn taking better control strategy. For future exploration, we would like to see whether using a generative model to imitate the underlying dynamics works better or not. So thank you, everyone. These are the two contact points for both of the authors. Please feel free to reach us if you have any questions. Hello, everyone. I'm Alif bin Abdul Qayyum, and my co-author is ANM Nafis Abir. Both of us are PhD students in Department of Electrical and Computer Engineering at Texas A&M University, College Station, Texas. I'm going to present our work solving Kuramoto oscillator model using physics-informed neural network. This work has been accepted to the third Muslims in ML workshop, co-located with NeurIPS 2024. Kuramoto model is actually a way of representation of collective dynamics, for example, neurobiological systems. This has recently gained attention in optimal experimental design. The origin of uncertainty in a Kuramoto model or collective dynamics comes from the unknown interaction strengths between different oscillators of a Kuramoto model. And as the objective here is to minimize the uncertainty, to quantify the uncertainty first, we need to solve numerous number of different Kuramoto oscillator models. However, solving numerous Kuramoto oscillator models might be challenging due to computational resources and also computational time. We evaluate physics-informed neural network as a fast solver to Kuramoto model, which can be used as an alternative to slow numerical methods. So Kuramoto model or Kuramoto oscillator network is actually a network of different number of oscillators which are coupled through either same or various coupling coefficient values, and the behavior of the overall Kuramoto model is governed by bunch of coupled differential equations. The reason behind coupled differential equation is each of those differential equations are interrelated through the coupling coefficients, which here is shown as a subscript I, j. The higher the coupling coefficient, the more the different oscillators are connected to each other and they behave in a synchronized manner. The lower the coupling coefficient, the less connected the different oscillators are, and they tend to behave in an unsynchronized manner. We use physics-informed neural network, abbreviated as PIN, to solve a Kuramoto model. So basically, we are trying to solve a bunch of coupled differential equations through physics-informed neural networks. PINs have recently gained attention for solving differential equations. So we use a feed-forward neural network model. Here, capital W represents the parameters of the neural network. We have the boundary conditions or the initial angular positions of the different oscillators represented as theta superscript 0. So when we train our PIN, what we do is we try to minimize a combination of two different losses. LB is the boundary loss, where the loss comes from the evaluation of the PIN network at the initial time point, and the residual loss LR, where we evaluate the PIN model at other time points, and we try to minimize the residual values. And the residual value is described as the showed equation here. And the overall objective is to minimize the weighted average of the boundary loss and the residual loss. Here are experimental results for two different Kuramoto models. The first row shows the actual solution of a Kuramoto model where the coupling coefficient is 0.1, and the PIN solution, you can see that it can capture the actual angular values at different time points, where we have a lower value coupling coefficient for the Kuramoto model. However, when the Kuramoto model has a high coupling coefficient, that means it tends to behave in a synchronized manner. The PIN model fails to capture the actual solution. Then we did a bunch of different experiments where our goal was to only minimize the residual loss, and we didn't have access to the initial conditions or the initial angular values of the different oscillators. Here, the objective was to see that whether we have a Kuramoto model that our PIN model is trying to solve, and if that Kuramoto model has a locking frequency, whether PIN can actually learn that locking frequency without even trying to learn the initial conditions. And as you can see that it can actually capture the locking frequency or the instantaneous frequency of different oscillators. So you can see that at initial time points, even though the PIN does not capture the actual instantaneous frequencies, however, eventually it actually predicts the actual instantaneous frequency for all the different oscillators. So the key takeaways we can say is the objective here was twofold. First, to see whether PIN can actually solve a Kuramoto model with all the initial conditions. It can when the Kuramoto coupling coefficient is smaller. However, it cannot when the coupling coefficient was higher. And if there is a locking frequency for the Kuramoto model, that is, it tends to behave in a synchronized manner, the PIN can actually learn the locking frequency or the instantaneous frequency of different oscillators, even if we don't train the PIN with the initial conditions. So thank you, everyone. This is the contact point for both of the authors. Please feel free to reach any one of us if you have any questions.